This video is going to be about similar triangles, so we're going to review some of the things that we talked about last class, and just to solidify the idea of similar triangles, and then go on to some of the application problems that we haven't had a chance to get to yet. So a couple of things to remember about similar triangles. So there's two main properties of similar triangles, and the first thing is that corresponding angles are equal. Basically that just means that all the angles inside the triangle are the same, and they're also in the same position. So we have a 60-degree angle next to a 20-degree angle. So that's the same for both triangles, and then there's a 100-degree angle at the top. So that one's pretty straightforward. It tends to be one of the easier relationships. The other one's a bit more difficult, but let's talk about that. So that's this idea that ratios of corresponding sides are equal. So corresponding sides are in the same position in each triangle. So we have side AB between 60 and 100 degrees, and in this triangle we have side DE between the 60 and 100-degree angle. So they're considered to be corresponding. We also have side AC, which is between the 60-degree and the 20-degree angle, and side DF, which is also between the 60 and 20 degrees. So these are corresponding sides. So that means that if I take the side length of AB and divide it by AC, I should get the same decimal number as if I divide the length of DE by the length of DF. So if I take the measurements 12 over 20, so the length of AB is 12 and the length of AC is 20. I should get the same numbers if I divide 3.6, which is the length of DF, by 6. So if I do that, I get 0.6, and on the other side I also get 0.6. So that's useful for me because it helps me find the length of sides that I don't know. So when we start using similar triangles, it means that if I tell you two triangles are similar, we can use these properties to help figure out the length of missing sides. If I were to write the notation for this, I would say that triangle ABC is similar to triangle DEF. So this little curly symbol in the middle tells me that they're similar triangles. If you don't see that, the triangles are not similar. Okay, so you need to look for that symbol to determine if the triangles are similar before you use these two important properties. So let's just test another side length ratio. So similar to what we just did in the last example, I could also say that side length BC is corresponding to EF, and side length AB we already know corresponds to DE. So let's test that ratio. So that means that side length of BC divided by AB should be equal to EF divided by DE. And so let's solve that one. So that's going to be 14 over 12 is the same thing as 4.2 over 3.6. So again, if I divide 14 by 12, I get a big decimal number, but if I round it, it's 1.17. And if I divide the other side, I also get the same decimal number, which I can round to 1.17. So this just proves that the ratio of these corresponding sides, or the ratios of the corresponding sides, are equal. Where things tend to get a bit tricky for similar triangles is if I give you two similar triangles, but I take one of them and I rotate it a little bit. So if I were to take this triangle and I were to rotate it, the properties of similar triangles still apply here, except we have to keep track of where the different angles are. So notice that here's my 60-degree angle, and here's the 60-degree angle in the triangle. Here's the 20-degree angle, and here's the 20-degree angle, and same thing with the 100-degree angle here at the top. So when the triangle's spun like this, they are still similar. We just have to be careful when we're picking corresponding sides. So to find the corresponding side for this length AB, I have to look for the side in my other triangle that is between the 60 and 100-degree angle. So that's going to be this one. To find the side that's corresponding to BC, I want to look for the angle that's between the 100 and 20-degree angle. So that's going to be this side length right here. So I can still use the same rules, I just have to pay close attention to which side lengths I'm using. And so you're going to see that in some of the examples that we'll do next. These practice problems are going to be from the worksheet that I left for you. So this is triangle FED and QRS from question number 4. And what I need to do is figure out how my triangle has been flipped. So notice that the triangles are in different positions, right? This one has been shifted a little bit. So I have to match up where the angles are. So I have this really steep side here, which is now actually over on the other side. So this really steep side here, QR, is now over here. And my other side here, RS, which is the long side, is over here. So the triangle's been mirrored. So that's important to pay attention to. How has the triangle changed? I know they're still similar because I've been given the symbol right here, right? So I know that they're similar, which means the angles are all the same and the side length ratios are equal. So I'm going to use the side length ratios to help me find my missing side here. So to set that up, I want to do side length QR over side length RS is equal to, so if I chose QR on top, I need to make sure I put EF on top, over DE. So QR is equal to 15, RS is equal to 20. And that should be the same thing as EF, which is 24, over X, which is going to be, let's call this unknown side here X, just to make it a bit easier. So 15 divided by 20 is 0.75. So I know that 24 divided by whatever this unknown side is has to also be 0.75. So the easiest way to solve this, if I were to figure out what number, in order to find out what X is, I have to do 24 divided by 0.75. And that's going to give me the value of X. So X is equal to 32. And I can double check that. So to double check my answer, what I can do is I can check that 15 divided by 20, which we know is 0.75, should be equal to 24 divided by 32. So if I type 24 divided by 32 into my calculator, it should also be 0.75, and it is. So I know that my answer is correct because the ratio between the corresponding sides is the same. Pay close attention here to where the X is in your problem, because sometimes the X or the unknown side is on top of the ratio, and when it's on top of the ratio, there's actually a slightly different procedure. So when the X or the unknown side is on the bottom, we do the 24 divided by 0.75. So this next problem is a different way of showing similar triangles. And so the way this works is, because these triangles are inside of each other, we know that they share this angle, right? This angle is going to be the same. We also know that because they're inside of each other, this angle is going to be the same as this angle, and this angle is the same as this angle. So we know that these are similar triangles because they're inside of each other. And we see that quite a bit. So what that means is, if we want to find our unknown side, so the side that we're trying to find is the length of this big side over here. So really here what we have are two triangles. We have our big triangle, which is QRP, and that has our missing side and a side length of 70, which we got from the bottom. Then we have our small triangle, which is DCP, and that has side lengths of 20 and 28. And so we already know what our corresponding sides are. I know that this side corresponds to this side, and on the bottom, this side corresponds to this side. So let's set up the ratio. If I want to choose the ratio for this one, let's say that the side length RP is over Q. Is this divided by QP should be equal to CP divided by DP. So when I say the RP, I'm talking about the length of this side. Now, in this case, what we know is that we don't know the length of RP, so we'll call that X. QP is 70. CP is going to be 28, and DP is 20. So I can use this ratio here to help me calculate the length of my missing side. Notice the difference here. X is on top of the ratio, whereas in our other example, X was on the bottom. So watch how the operation changes. To find the value of X, I have to take 28 divided by 20, and then multiply that by 70. So if I do that, 28 divided by 20 is 1.4. Multiply that by 70. And I get the length of my missing side, which is 98. And that actually makes sense, because if you think about it, triangle QRP is the bigger triangle, and so this side should be longer than 28. But I can check it, like we did in the last example. So to check it, 98 divided by 70 should be equal to 28 divided by 20. And so if I do that, I get 1.4 and 1.4. So I know my answer is correct. So again, just to recap, pay attention to where the x is. If the x is on the top of your ratio, you're going to multiply them to find the missing side. If the x is on the bottom of your ratio, you're going to divide. Now the other option here is if you didn't want to divide, if you always just wanted to multiply, like in this example, you could flip the ratio. So I could take this ratio and I could write this as 20 over 15 is equal to x over 24. So all I did is I flipped everything from the bottom to the top and everything from the top to the bottom. And so now I could work with this ratio over here, which has the x on top, and I could do the multiplication. The last thing to cover are just some application problems. So how can we use similar triangles in real life? So there's two ways that we're going to look at. The first one is by using the shadow created by the sun to estimate the height of objects. So since we know that if we look at two objects at the same time of day and we measure their shadows, so keep in mind it's at the same time of day, so the sun is at the same height hitting both of these objects. And that means that the sun's hitting both of these objects at exactly the same angle. So this angle right in here is equal. Since both of these objects are straight up and down, that means that this is a 90 degree and this is 90 degrees. So since two of the angles are the same in our triangle, it means that the third angle up here is also equal. So that makes these two triangles similar. So what we can do is we can use the side length of this shorter shadow. Say this was a person standing up. I know the height of the person, I know the length of their shadow. So I can use that ratio to help me predict the height of this tall clock tower if I just measure the shadow. Next way we can use similar triangles is if we want to use a mirror to measure the height of objects. So again, similar to optics, the incident ray, so me looking down at the mirror, is the same angle as the reflected. So angle of incidence is equal to the angle of reflection, so which means these two angles are equal. Since we have a 90 degrees here and 90 degrees here, those two angles are equal, so the third angle must also be the same in both triangles. So all the angles are equal, so we have two similar triangles. So now I know that I'm able to solve the problem. So if I read what I'm given up here, the height of the ground, or the height from the ground to Jim's eyes, is 150 centimeters. The distance from the middle of the mirror to Jim's feet is 100 centimeters. The distance from the mirror, the middle of the mirror, to the point directly under the traffic signal is 450 centimeters. So what I can do is I can use these similar triangles to find my unknown height. So in this case, this side corresponds to this side. And this side corresponds to this side. So if I work this out, then that means that 150 divided by 100 should be equal to my unknown height, let's call this x, divided by 450. So x is on top, so what I need to do is I need to divide 150 by 100, so I know that that's going to be 1.5. Multiply that by 450, and that should give me the value of x. So the height of the tower is 675 centimeters. And I'm going to write a little statement to summarize that. Actually, sorry, it's not the tower we're talking about anymore, it's a traffic signal. So let's talk about that. So the height of the traffic signal is 675 centimeters. Let's go back and solve the problem with the clock tower. So again, in our clock tower, the height of this stick corresponds to the height of the tower. since they're in the same position, and the length of the shadow corresponds to the length of this shadow. So if I were to set up the ratio for this, the height of the tower, which I don't know, divided by 8 meters, because I know that the length of the building shadow is 8 meters, divided by, or is equal to, the height of the stick, which is 3 meters, divided by the length of the shadow, which is 1.5. I don't really need to write the units in my ratio, and I usually don't because it just complicates things a bit. So I usually just leave them like that with just the numbers. So I'll divide 3 by 1.5, and that gives me 2.5. Or sorry, 3 divided by 1.5 gives me 2. That means that x is equal to 2 times 8, or 16 meters. So write a statement, therefore the height of the tower is 16 meters. So here's another application of the similar concept. So I have a tree, which is right here, that casts a 24-foot shadow. At the same time, a yardstick, so it's American, they call it a yardstick instead of a meter stick, casts a 2-foot shadow. Find the height of the tree, which they've already called x for us. So to solve this problem, I have to remember that this side corresponds to this side, and this side corresponds to this side. Because again, we're on the same time of day, the sun is hitting both objects at the same angle, so we know that these are going to be similar triangles because this angle, or the angle of the sun, has to be equal. Our 90 degree angles are equal, so that means this top angle is also the same in both triangles. So I can set up the ratio. If I want to know the height of the tree, it's going to be, I know that the length of this side divided by the length of this side is the same as the length of x divided by 24. 3 divided by 2 is 1.5, and 1.5 times 24 gives me my unknown length. So I know that the x is 34 feet. Write a quick statement that therefore the height of the tree is 34 feet. We'll do one more, and then I'll let you work on the rest on your own. So the thing to remember about this one, we're being asked to find the height of the giraffe, who's here behind the cage. So we don't know the height of the giraffe. We're using the mirror strategy here, so we know that our inside angles here are equal. We know that our 90 degree angles are equal. So that must also mean that these top angles are equal. So we have two similar triangles. If I think about corresponding sides, this height is the same as this height, and the bottom height is the same as the bottom height in the other triangle. So they give me down here the distance for these bottom lengths, but notice that for the height of the person, they've given me the height as 5 feet 3 inches. So that's two different units. So what we want is for this to be in the same unit. So what I have to remember is that if I convert 3 inches to feet, so there's 12 inches per foot, so 3 inches then is going to be a quarter of a foot. So this is actually equal to 5.25 feet. So when I'm doing my conversion, I have to be careful. This is the only problem where you need to do that, but just make sure that you're using the same unit. If I set the ratio up now, 5 1/4 or 5.25 divided by 5 has to be equal to the height of my giraffe divided by 15. So I get 1.05 for this ratio, so that multiplied by 15 must be the height that I'm missing. So the height of the giraffe is 15.75 feet. Now if I wanted to convert it back to the measurement like I originally had, 0.75 feet, so 3/4 of a foot, is going to be equal to 9 inches. So we're going to get 5 feet 9 inches. You don't really need to worry about the unit conversion here, but we'll talk about that for our summative activities, so it's just good practice. So if you wanted to be technical here, you could say that the giraffe is 5 feet 9 inches tall, or you could say 15.75 feet. So remember that 9 inches is the same thing as 3/4 or 0.75 of a foot. I'll leave these other problems for you to do on your own. The last one here is a little bit challenging. The only hint I'll give you for this one is if you let this length, which is the length we need to know, we're going to call that x. And I'll leave you with that and see if you can figure it out from there.